Hello, this is Jack Jackson. In this video, we're going to be introducing some finite geometries. Okay, the postulates that we have presented so far in the playlist that you've seen earlier in this playlist and the first one have only dealt with existence and incidence relationships. In other words, they either state the existence of some geometric figures with certain properties, postulate 3 does that, or the rest of them, they are conditional statements, which say that if a certain geometric figure with certain specified properties exists, then other geometric figures also exist with certain element or subset relations with the given figures. Since there's no concept of distance or betweenness associated with these instance postulates, we can easily create multiple finite geometries which model them. In fact, below we prove proposition 1, and in this process we introduce a finite geometry containing exactly 4 points, 6 lines, and 4 planes, which satisfies the given initial set of existence and instance postulates for neutral geometry. However, remember that Euclidean geometry, which has infinitely many points, also satisfies these postulates. So clearly this is not a categorical set of postulates so far. By selecting some of the initial instance postulates and perhaps modifying them slightly, we can explore several geometries. We should be careful to include at least one existence postulate in our set of postulates so that we are guaranteed to be talking about something besides just the empty set. Otherwise, almost any conditional statement would be vacuously true in the geometry. For example, if we say that P is a plane, then P contains a non-collinear set of 3 points. If there are no planes, then that statement is true. Okay, it's called vacuously true. Anytime you have an if-then statement, if the if part, the hypothesis, is false, doesn't matter what comes after the then. If there are no planes, the conditional statement then the hypothesis of the conditional statement is false and the statement is true regardless of what the conclusion of the statement says. This is a vacuously true statement. In general, a conditional statement, if hypothesis then conclusion, is true if the hypothesis is false. So it's kind of a little weird thing, but that's the way it works. We will assume, without explicitly stating it as a postulate, that if they exist, lines and planes are sets of points. I explicitly state that in my set of postulates for unified geometry, but in the geometries we're going to go below, we will assume that if it's convenient. So that allows us to use the language and notation of set theory when we find it useful. When we specify a model for a finite geometry, we list the set of points, the set of lines, and the set of planes. Some of those may not exist, like, for example, some models, there won't be any planes. And remember that lines and planes are themselves sets of points, so the set of lines is a set of sets, as is the set of planes. The list of sets is the model. We can also build an illustration of the model, a picture, a drawing, but be careful when interpreting the illustrations. We often use Euclidean line segments or Euclidean curves to indicate the lines in the model. However, remember that these only indicate incidence at this point, so points of the geometry are only those specified in the model, particularly when we're working with a finite geometry. All geometries should contain a non-empty set of points, but they may or may not contain non-empty sets of lines or planes. Remember that the illustration is not the model. Okay, the model is the list of points and lines and planes. We next consider some very elementary axiomatic systems resulting in finite geometry with very few points and lines. In fact, these are kind of so small they're pretty boring, but for all of our finite geometries, we will use the implied postulate that lines are sets of points. And note that the postulates in these geometries are variations of the incidence postulates that we have in our set of postulates for unified geometry. Once again, note the model consists of the set of points, lines, and possibly planes. The illustration is a physical drawing depicting the model. Now, you might ask, well, why are we even studying this? Okay, what do we get out of studying finite geometries? Well, by studying finite geometries, whether you're a high school student or junior high student studying high school geometry for the first time, or like my students, you're studying college geometry, there are some useful things that come out of studying some finite geometries. And by studying them, we'll be achieving these following goals. We will be gaining an understanding that there are multiple geometries besides Euclidean geometry, including many with only finitely many points. And we can start by practicing writing some detailed proofs, starting with some very elementary but unfamiliar geometries. So the fact that they're unfamiliar is good for us because it creates what we call cognitive dissonance. It creates a setup to where we're in unfamiliar territory, and that's where you really start learning things, is when you have to deal with some unfamiliar ideas. But on the other hand, they're very elementary, so that there's really not much to them. There's only just a few postulates to work with, so there's not much there to work with, and it turns out there's usually just only a few points and lines anyway. From this, we will gain a deeper understanding of exactly which combination of postulates lead to various results. So we'll look at, well, what happens if you don't have this postulate? Can you get something different? Or what causes what? What is it that makes certain things happen? Is it just one postulate that makes it happen? Or is it the interplay among various postulates? And we'll also gain a deeper understanding of the foundations of Euclidean geometry by studying these non-Euclidean geometries. So let's start with the most basic one I can think of. Here is a one-point geometry. Postulate 1, there exists exactly one point. Postulate 2, each point is on exactly one line. So the model for this, the set of points, is the point A only, and the set of lines is the set containing A. And so that is the points and the lines. There's not much to it. This set of postulates has the following important properties. It's consistent, so there exists a non-empty model that exhibits all the given axioms. Axiom is another name for postulate. It is independent, so there is no axiom that can be deduced from the others. Replacing any axiom with a contradictory axiom produces a non-isomorphic model. It's categorical. All models are isomorphic, essentially the same. We could name the point a different name, but it's basically the same thing. However, this is extremely boring. There are absolutely no interesting propositions in this geometry. There's nothing to it. So let's make it, well, really not much more interesting. Let's look at another one. A two-point geometry. There exist exactly two distinct points. We'll call them A and B. Each two distinct points are on exactly one line. So the model for this is the set of points is the set containing A and B, and the set of lines is the set containing the set A and B. The set A and B is a line, right? So the entire universe of this thing is one single line. Now, notice how we've illustrated this. There's a shape here that appears to be a Euclidean line segment. This does not indicate a Euclidean line segment in this case. There are only 2 points, A and B. It's just by connecting them up like this with some sort of curve, line segments as good as anything else, it shows us that these 2 points are incident with each other. That is, they are on the same line. Okay? And so the set containing AB is the entire line. There are no points between A and B. There are only 2 points in the entire geometry. Again, this one's too simple of a geometry to be of much use. All right, let's get one that's mildly better here. A 3-point geometry. Postulate 1, there exist exactly 3 distinct points, A, B, and C. Postulate 2, each 2 distinct points are on exactly one line. Another way to say that is, given any 2 points, there is exactly one line containing them. Or another way to say this, if you know, x and y are 2 points, then there exists exactly one line containing x and y. That's an if-then version. Postulate 3, not all the points of the geometry are on the same line. That's going to be necessary to eliminate one possibility. And number 4, postulate. Lines are sets of at least 2 points. Okay. So now what we want to do is build up a model about this, of this geometry, and it's simultaneously we're going to prove a few, well, interesting is too strong a word. We'll say mildly interesting results for this geometry. And here we're going to make use of a multi-column format for the proof in which a sequence of statements is made and the supporting reasons are made explicit. And we'll also accompany this with a third column that has the model being built up a little bit at a time. And unlike most proofs, when we establish a model, we do not start with the hypothesis of a proposition. Instead, we start with an existence postulate. So this is a different kind of a proof. So you should start a proof with an existence postulate only when building a model such as this. We only have these 4 postulates with which to work, so it should be fairly straightforward to see how to link them together to form a model. So where are we going to start? We got to start with which one of these is an existence postulate. Let's read them backwards with number 4. Lines are sets of at least 2 points. So that says if L is a line, then L equals a set containing 2 points. Okay? So this one says if you've got a line, then there are 2 points that make up that line, no more, no less. Again, that's an if-then, conditional. Postulate 3, not all the points of the geometry are on the same line. That's really conditional as well. It doesn't guarantee that we have any points or lines. What it does say is that they're not all on the same line. So if you have, there is no line containing all the points. If you have 2 points and then you have, well, it tells you what you don't have. You don't have a line containing all of them, right? So what that also says is if you have a line, then there exists a point that's not on that line. That's another way to rewrite that as an if-then that's equivalent. Postulate 2 says each 2 distinct points are on exactly one line. So that says if you have the 2 points, then you get the line containing them. Notice postulate 4 says if you have the line, then you get the points. See the difference? They're sort of backwards from each other. Which one for what you're given. Postulate 2, you start with 2 points, you conclude that you get a line that contains them. Postulate 4 says you start with the line and then you end up with the 2 points. But postulate 1 is an existence postulate. Postulates 2, 3, and 4 can be rephrased in an if-then, but postulate 1 is an existence postulate. So that's where we're going to start. There exist exactly 3 distinct points A, B, and C. And the reason is, well, that's what postulate 1 says. So this is our model so far. It's not complete yet, but it does satisfy statement 1, which is postulate 1. Now, what can we use? All right, let's look up here. Well, now we know we have points. We don't necessarily have any lines left. Which one of these starts with points? Well, postulate 2 says if we've got 2 points, there's a line containing them. So let's take the 2 points A and B, which are guaranteed from step 1, all right? So we're using step 1. That satisfies the hypothesis of postulate 2, and the conclusion says there's exactly one line containing them. Let's call it L. Now I claim that L is exactly the set A and B, no more, no less. Not subset here, but equal. And this goes by statements 1 and 2. And it's also going to use postulate 3. There's only one more point, C. If C was on L, then that would violate postulate 3, which says not all the points of the geometry are on the same line. So we use postulate 3 to show that that line, L, or L1, is exactly the set A and B. We're going to do a similar setup using points A and C. There's a line L2, which is the set AC. And then, again, the same reasons. It's exactly that. And then for the similar reasons, you can take points B and C and make one line L3 that contains those 2. So now we've shown that there exists at least 3 lines. And I'm going to say that, well, there's got to be exactly 3 lines. Why not? Why couldn't there be more lines? Well, we've already eliminated the possibility that there's a line that contains all 3 points. What about a line containing only 1 point? See, that could possibly be a possibility, except for postulate 4. Postulate 4 says lines are sets of at least 2 points. They turn out to be lines of sets of exactly 2 points, as we see here. And so there are exactly 3 lines. There they are. We can label them as L1, L2, and L3, but also as these sets. And we can also prove something else. Each pair of lines intersects in exactly 1 point, so there are no parallel lines. And you can easily just see that by just looking at all the combinations of intersections. You can see it in the picture, and we can do it, just do them. And then we put this symbol at the end. That little black square is the proof. It's a symbol at the end to indicate that we've succeeded in proving what we've set out to prove. We're done. The proof's over. You can get this symbol from the insert equation symbol from Word. So get up here where I can see the ribbon. If you go to Insert, and then let's see, I have it here. I'm not sure. I've modified some of my ribbons, so I'm not sure if yours is there. But if we go to, they can go to Insert Symbol there, go to More Symbols and find it. There's actually an Insert Equation symbol, so menu as well. I have that actually on my home screen. That's kind of nice. If you can modify your ribbon to include that. Here has, basic math things, Greek letters, letter-like symbols, and so forth, but it's on the first page right there. You can get to this if you go to Insert an Equation and look at it. But in any event, you want to put that there, or if you've got one of my documents open, you can just copy and paste that. So this symbol takes the place of the common abbreviation QED for the Latin quod erat demonstratum, which loosely translated means that which was to be demonstrated. Speaking in Latin terms, I will regularly make use of the abbreviations IE and EG. IE is an abbreviation for the Latin term id est. It basically means that is, or in other words. Similarly, EG is an abbreviation for exemple gratia, which means for example. And notice that in the process of what we've looked at, we have proved a couple of propositions, a couple of theorems. Proposition 1, there exist exactly 3 lines. And there they are. L1 is the line which is the set containing A and B, nothing more, nothing less. L2 is the set containing A and C, and L3 is the set containing B and C. And we've also proved proposition 2, each pair of lines intersects in exactly 1 point. Here's our model. The set of points is the set A, B, and C. The set of lines is the set containing the set AB, the set containing A and C, and the set containing B and C. Each one of those is a line. They're also notated as L1, L2, and L3. There are no planes in this one, so we don't have to worry about that. This would also be consistent if you said that there was one plane containing everything. And there's an illustration. Once again, these line segments are not part of the these Euclidean points in between here are not part of the model. They're only the 3 points, and these indicate incidence only, that they're on the same line. Consistency, notice this system of postulates is consistent since we were able to generate a model satisfying all the postulates. And you might go through each postulate and verify that the model satisfies the postulate. Their independence. Each postulate was used in the proof construction above, which is an indication that all of them are independent and needed for the proof model derivation. However, we can prove that each postulate is independent of the others by removing it and showing that there exists at least one non-isomorphic model satisfying the remaining postulates. Notice that our 2 propositions fail in each of the models below, so we're going to do this. And so it is the interaction of all 4 of the postulates which makes these propositions true, And a valid proof of these propositions will have to use all four postulates as reasons. So each of the following models satisfies all the postulates except for the one that was removed, which it violates. And these models, along with the original model satisfying all four postulates, shows that the removed postulate is independent of the other three in the set. Since we can do this for each of the original postulates, this makes the entire set of postulates an independent set of postulates. And you should be sure that you understand how the model violates the indicated removed postulate, which is not a postulate anymore, but satisfies the remaining three postulates. So if we remove postulate 1 says there exists exactly, There exists exactly 3 points, but we want to keep the others. And I claim that this model here works. This one has 4 points. It has lines AB, AC, AD, BC, BD, and CD. So every line is a set of exactly 2 points, and given any 2 points, there is exactly 1 line containing them, and not all the points are on 1 line. So I think we satisfied everything except for the fact that there's exactly 3 points. So postulate 1 is independent of the other postulates. One way we could satisfy postulates 1, 3, and 4, but not 2, is just to have the 3 points A, B, and C and not even have a line. So you got to have postulate 2 to guarantee that there actually even is a line. So we could make postulate 2 false by making a model where at least 2 points are there for which there's either not a line containing those 2 points or that there's more than 1 line containing those 2 points. So there's actually several different options of ways we can make this one fail. Postulate 3 says that there can't be 1 line containing all the points. So if we want that to be false, we need a line containing all the points. And here's a model that does that. We have the points A, B, and C, and the set A, B, and C is 1 single line. Notice it still satisfies the others, right? Lines are sets of at least 2 points, in this case 3 points. It still satisfies 2 distinct points on exactly 1 line, and there's still exactly 3 points. So 1, 2, and 4 satisfy, but not 3. Postulate 3 is independent of the other 2. And this last one allows some 1-point lines, which I've indicated by the little circles here. The points are A, B, and C, and the lines are AB, the set containing AC, the set containing BC, but also the set just containing A, and the set just containing B, and the set just containing C. So there are actually 6 lines here. Some of them have 1 point per line, some have 2 points per line. That violates what was postulate 4. It's not a postulate in this geometry, but the other 3 work, so postulate 4 is independent. So you can see why you need all 4 if you're going to get this model up here, and if you're going to get these propositions. Because both of these propositions here is false. They may be false down here, at least some of them would be. So it turns out that the original set of postulates is a categorical set of postulates, since any other model we can make for geometry would be isomorphic to the model we've developed here. It's a little harder to actually prove that, but that's true. So let's talk a bit about what does it mean for 2 mathematical objects to be isomorphic? What does that term mean? So a general broad definition of homomorphism, let's do that first, is a structure-preserving mapping. Mapping is another word for function. And what this means depends on the context. In abstract algebra, we talk about a thing called an algebraic group. There's a whole area of mathematics called group theory. In fact, my PhD is in group theory. In an algebraic group, there is a set with one operation which obeys some algebraic conditions. So therefore, a group homomorphism is a function f mapping a group G into a group J, where G and J are groups. They're sets with these conditions, and they come with an operation, so that the function preserves the multiplication. It preserves the group structure. So what that means is, if you take an element G and an element H that are in the group G, and you multiply them together using the multiplication in G, you'll get another element in group G. If we find its image under F, we'll get a single element in group J. Well, what we can do is then apply the F to G and H independently. Then F of G is an element of J, and F of H is an element of J. And if we multiply them with the multiplication or the operation that's in J, we have to get the same thing here. So that's what we mean by preserving the multiplication. Okay? And G and H are any elements of the domain group G, and the star G and star J are the group operations in G and J, respectively. So in an algebraic ring, it's a set with two operations, so the ring operation must preserve both operations, sort of a similar manner that we did here. A vector space homomorphism must preserve vector addition, vector multiplications, and scalar multiplications. So those are come from the areas of abstract algebra and linear algebra and so forth. But what would a homomorphism mean between two geometries? Well, what do we have in geometries? Really, we have incidents, right? We have lines, planes, and points, right? And what we have is basically a set of points. And then, but we have some incidence relations, so we have sets of points, sets of lines, sets of planes, and then we have some subset and element relationships. So a geometric homomorphism must preserve that. So it's a function mapping points of one geometry to the points of another geometry, such that points are mapped to points, lines are mapped to lines, and planes are mapped to planes in such a way as to preserve incidence. In other words, if A and B are points of line L in the domain geometry, then F of A and FB have to be points of the line F of L in the second geometry, and similarly for planes. Now, an isomorphism is a bijective homomorphism. Bijection means it's both injective, which is another word for one-to-one, and surjective, which is another word for onto. So it turns out that if two mathematical objects are isomorphic, if and only if there exists an isomorphism from one to the other, and isomorphic objects are in essence the same object with a renaming or some kind of different notation. So in their essence, they're the same. So if a particular set of postulates is categorical, any two models for that geometry must be isomorphic. In the case of the three-point geometry, we can change the appearance of the diagram if we want, and we can even relabel the points, calling them anything we want, but the end result will really be exactly the same as we have here for all geometric purposes. Notice that the proof above was given in a multi-column format. We could have also written the same proof in the more flowing paragraph format as follows. Here's the same proof. Proposition 1, there exist exactly three lines. L1 is the sets containing A and B, L2 is the set containing A and C, and L3 is the set containing B and C. By postulate 1, there exist exactly 3 points called A, B, and C. There are exactly 3 pairs of these points, the set containing A and B, the set containing A and C, and the set containing B and C. Each of these three sets of 2 points is contained exactly one line by postulate 2, but since postulate 3 guarantees that there is no line containing all 3 points, no point can be added to the lines containing each of the pairs above. Therefore, each of the 3 sets above is a line, and they are clearly distinct. Postulate 4 eliminates the possibility of lines with fewer than 3 points, so these 3 sets of 2 points are exactly the set of lines. Proposition 2, each pair of lines intersects in exactly 1 point. Well, once we have the full list of lines, this is easy. By proposition 1, the set of lines is exactly what we said it was there, and there are only so many intersections to look at, and we can find that they all intersect in exactly 1 point. Next video, we'll come back and look at a little more interesting geometry that has 4 lines in it.